we're going to build broadcast. Broadcast is a very basic, very important function, so we're going to start with broadcast. The most basic broadcast, the most simple one, is called unreliable broadcast, or best effort broadcast. Basically one node, so here we have 4 nodes, and the time is going from left to right. One node has like a for loop, and it sends messages to all of them. But nodes can crash, so these red X's can crash, or messages can disappear, okay? So maybe this node crashes here, and before it's able to send this message. So that means P2 and P4 will both deliver the message, but not P3, because of this crash. So this is a very unreliable algorithm. If you have crashes, it's really not sure what's gonna happen in this algorithm. Okay? So we want to do better than that. This is really not good. So we're going to make improved broadcast algorithms. So even if you have crashes, they do a lot better. So the simple one, which is done like the unreliable, is called best effort broadcast. This is the most simple, naive one. This one will only be reliable if the sender is correct. That means if I send a message to everybody, and if I don't fail, then everybody will deliver. But if I fail, then they won't. Okay? The better one is called reliable broadcast. This will guarantee the reliability even if the sender crashes. Okay? That means no matter what happens to the sender, either all nodes will get the message or nobody. It's nothing in between. It's all or none. So if you get the message, you know that everybody else got it. Okay? So that's reliable broadcast. And then there's a very powerful extension called uniform reliable broadcast. So what this means is that we're going to talk about failed nodes too. If a node crashes, but before it crashes, it gets the message, then we know that everybody got the message too. So the uniform reliable is a more powerful version of reliable that also works for failed nodes. So I'll talk about that later. And then there's more special ones. FIFO, reliable broadcast. This is if you're sending multiple messages, 2 messages, then they will arrive in the same order that you send them. Okay? If in one node I brought 2 broadcasts, then the first one will arrive before the second one. The order will not change. So FIFO means first in, first out. It means that the order is not changing. And then a final one is causal reliable broadcast. This basically respects causality. And this is like for a chat room. If I receive a message and I reply to that message, then a third guy will receive the question before the reply. So the message order will always respect causality. So this is more complicated to do, but it's important, like for in a chat room or for Facebook. If I send a question on a chat and somebody replies, the third guy who's listening should get the question before the answer, right? Well, in order to do that, it has to respect causality. If you don't work, if the algorithm is not made for that, then the message order can flip around, okay? And you can receive the answer before the question, which is kind of dumb. You receive an answer, so what's going on here? And the question comes much later. It's kind of messy. So if you want to avoid that, you need causal reliable. So you see there's a lot of possible ways of doing broadcast. It's such a simple thing, broadcast. Okay? So we're going to talk about broadcast now. So the way to do it is we're going to start by specifying and then we implement. So the broadcast is a box. It's an algorithm that we built. So there's a box here on every node, and it has a request and an indication. Remember, the request is going down, and the indication is the answer coming back. So the request is a best effort broadcast. So, and the best effort broadcast message, and a best effort broadcast deliver. So when the answer comes back. So we send a message. When you deliver it, you also know where it's coming from. And then we have properties. Remember, we like to make properties. So there's 3 properties for the broadcast. So basically, here they are. Validity, no duplication, and no creation. So this is the art of distributed algorithm, of making a good specification. So best effort validity, if PI and PJ are correct, if both nodes are correct, then any broadcast by PI is eventually delivered by PJ. So that means that if any one of these nodes crashes, we can't say anything, of course. This is an if-then. It's conditional. It's conditional on the nodes being correct. And that's why it's called best effort. If PI or PJ crashes, this says nothing. Okay? That's important to understand. This only says something if the nodes are correct. That's why it's called best effort, which is actually the weakest broadcast. And then no duplication. The message is no message delivered more than once. So maximum once, and no creation, no message delivered unless broadcast. So all 3 of them together are defining the best effort broadcast. And of course, you know immediately which one of these is safety and liveness. Remember that? I'm not forgetting that. So the one is what? What is it? Safety or liveness? First one. Quick.
Liveness.
Liveness. Okay. Eventually delivered. Good things eventually happen. What about second one? No duplication. Somebody else. Safety. Because if you deliver twice, you break the system. What about this one? No message delivered on broadcast. Safety or liveness. Another person.
Safety.
Why?
Because you cannot create what you can.
Well, if you do create, you've broken the system. Yeah, exactly. You can. That's just another way of saying it. You have to say why it's safety property. Yeah. Safety property means you can actually break the system and it stays broken after that. So okay, so now we go, and we can. Here's an example. Here I broadcast. So P1, P2, P3, P4. None of them are crashing. Okay. Is this allowed according to the specification? Which means I deliver on P2, I deliver on P4, but I don't deliver on P3. Is this a correct behavior according to this specification? Remember what it says here? If PI and PJ are correct, then any broadcast by PI is eventually delivered by PJ. Is this satisfied here? What do you think? Another person answer. Yes.
Oh, it's not.
Why not?
Because if nobody crashes, P3 should receive the...
Yes, this does not satisfy BEB1. Okay. What about this? So here, it's almost the same except for P1 is crashing here. Is this allowed by the specification? Yes or no? Another person. Somebody in the back. No? Is it allowed or not? Remember the specification. I recall the specification for you. If PI and PJ are correct, then any broadcast by PI is eventually delivered by PJ. Is that satisfied here? Yes or no?
Yes.
It's an if. I give you a hint. It's an if. There's a condition here. If this condition is false, then this rule is always satisfied. Okay? Because it's an if. Be very careful about ifs in specification. So, in order for this to say something, both PI and PJ have to be correct. Otherwise, it says nothing. Okay? That's very important to understand. So, what about here? Now you can tell me, right? Does it satisfy?
Yes.
Yes! Okay? Because P1 crashes. Okay? Best effort gives no guarantees that the sender crashes. Okay? So I'm not going to give the code because it's just a loop, but I will give code for the next one. Now we go to the next one. So best effort is a very weak thing. Huh? The specification is very weak here. It's not saying very much because of this if. If the two nodes have to be correct, otherwise nothing. So reliable broadcast says more. It does best effort, but it does more. Even if the sender crashes, all or none of the correct nodes get the message. That means if one of the correct nodes gets it, all of them get it. Okay? It's not possible for a subset to get it, unless that subset is empty. Okay? So, reliable broadcast, that's the next one. I'm going to give code for this one. So the interface is almost the same. You have a broadcast and you have deliver. It has 4 properties. The first 3 are the same as best effort. So it's going to do the same, but it's going to do more. It's going to do what I call agreement. If a correct node delivers M, then every correct node delivers M. That's a very strong property, yeah? That means if you get the message, then you know that everybody else got it, okay? That means one node can deduce a lot. If I get the message, I know all the correct nodes have gotten it. In best effort, you could not deduce that, huh? If I get it, I don't know anything about the others for best effort. But here, all the nodes are connected together, huh? Okay? It's like magic, yeah? How does it work? How can we make an algorithm that does that? All the nodes are connected. If one of them gets it, they all get it. It's pretty nice, huh? Actually, we can actually change a little bit the specification. So this is an example also of specification engineering. Because of this one, the 4, we can actually simplify the 1 a little bit. Okay? We can say here, if a correct node broadcasts M, then itself eventually delivers M. Okay? Because this together with the 4 will give you this one. Huh? So this one is actually more complicated, the original one. Huh? We can actually simplify a little bit if we take RB4 into account. That's just an example of specification engineering. Simplify. It does not change the meaning. Eh? Some examples now to see whether you understand. Is this allowed? So P1 broadcasts, but it crashes, and none of the other nodes delivers the message. Is this allowed in reliable broadcast? Is it allowed? So the so there's if a correct node delivers M, then every correct node delivers M. Notice again, there's an if. When you see a specification, you have to immediately check to see if it's if then. Okay? There's a condition here. If a correct node delivers, then every correct node delivers. So what about this example?
Yes.
If a correct node delivers, so does it satisfy?
Yes.
Yes, because no correct nodes are delivering. So the if is actually true. Okay? Yes. What about this one? If a correct node delivers, all correct node delivers. Here it delivers here, but then it crashes. If a correct node delivers, then all correct nodes deliver. But P4 is not a correct node, because it crashes. P4 is not correct, and P1 neither. P2 and P3 are correct. So this is?
Yes.
Yes. Okay, good. What about this?
Sorry.
Sorry?
A question for just before it crashed,
Yeah.
P4 had delivery.
Yes, but
then
the algorithm is not finished. So P4, even though it delivers before the crash, it's not a correct node. A correct node is a node that crashes. So the deliver might happen before the crash. So we're not sure actually. Or maybe it crashes before it can deliver. Actually, a correct node is actually very flaky. We're not really sure what happens here. But it's a good question, because when we talk about uniform reliable broadcast, then this case is very important. Then we will look at the delivery even if it crashes. So your question is actually related to uniform reliable. So uniform means that it actually is the same for crashing and correct nodes. It's uniform for crashing and non-crashing. So here, the node crash, we don't say anything. But in a uniform algorithm, we are also going to say a thing about the crash, about this one. Okay? So wait until we talk about uniform, and then you'll see that your question actually is important. Okay? So this is allowed. What about this? Is it allowed? So here again I deliver and I crash, but here P1, P2, P3 are all three of them correct. Okay, this is actually a little bit more subtle. If you look at the specification, if PI and PJ are correct, then any broadcast by PI is eventually delivered by PJ. Or another way to say it is if a correct PI itself eventually delivers M. So, how does that fit with this one? Does this satisfy the specification? No, why not?
Because the P1 broadcast M, but P2 and P3 don't receive them?
Because P1 is correct. Yeah, and P1, P2, and P3 are correct. So P1 broadcast M, P2, and P3 should deliver. They should get it, okay? But they don't.
Yes.
So this is not following the specification. Okay?
And if they receive them but P4 crashes, is it still correct?
Yeah.
Okay.
Sorry. If who?
If P2 and P3 receive them, P4, but P4 crashes.
But it doesn't matter. What
Okay.
P4 does has no effect on P2 and P3. If you're talking about P1 and P2, both of these are correct. That means P2 must deliver.
No.
It's not. We don't care about P4. Huh? P1 and P2 are correct. That means P2 must deliver, but it doesn't. So it's wrong. Okay. So for every pair, you have that. If the two nodes are correct, it must deliver. So even if the P4, it doesn't matter with the P4. The P4 is not a problem here. The problem is P2, P3, which are not delivering. And P1 also, which has to deliver to itself.
So if the P2 and P3 receive because they'll say yes?
If P2 and P3 deliver, but P1 does not, then it's still a problem. P1 also has to deliver to itself. Huh?
Okay.
All of the correct ones have to deliver. Okay. P1, so if any one delivers, okay, yeah, P1 is correct here. So that's why it's like that. Huh? So P1 is correct. If a correct PI broadcasts M, it itself has to deliver M. Okay. Notice I say deliver, huh? I don't say receive. Deliver means that there's an indication here. Deliver means that it delivers it to the application. It doesn't talk about this. Huh? It talks about the output. Huh? So it's not because the node receives a message. That's not what I'm talking about here. I'm talking about delivering the message to the application. So it has to come out here, huh? Okay? So delivery is not exactly the same as a node receiving a message, huh? I don't care about that. What I care about is, does the application get the message? And that's why it's called delivery and not receiving, okay? Just to need to, okay? No. Here's an interesting one. So P3 crashes here. 1 and 2 and 4 are correct. And 1 and 2 and 4 all deliver. But P3 does not deliver. Does that satisfy the specification?
This is what we discussed. The last one.
Sorry, say it.
The last one we asked P2 and P3 received, and you said it's still not okay because P1 didn't receive. For this one, it's like P1 still receiving.
P1 is receiving here, huh? Is delivering, huh?
Yeah, this is only
And P2 is delivering, and P4 is delivering. Only P3 is not delivering, huh? Okay? So what do you think, huh? This is fine, huh? It's a reasonable execution of the algorithm. This is actually what we wanted to do.
In this case, it's okay because P1 delivers to himself
Yeah.
and to every other, even if P3 crashes and doesn't receive.
So if a correct node delivers, then all correct nodes have to deliver. So P2 and P4 are correct nodes. If P2 delivers, they all have to deliver. If P4 delivers, the others have to deliver. If P1 delivers, they all have to deliver. But only the correct nodes, huh? P3 is a crash node, so we don't care.
Okay.
Okay? If in the uniform algorithm, we will care about crash nodes, huh? But in the regular reliable broadcast, we don't care about the crash nodes, huh? We're only looking at correct nodes. Okay? So now, here's another version. So here we talked about reliable. I'm going to give you the code for these, huh? But first I want to talk about uniform reliable broadcast. So you understand reliable now, huh? Reliable means it's all or none, but only the correct nodes, huh? Either all the correct nodes or none of the correct nodes. Okay, that's reliable broadcast. And we don't care about the crash nodes. But maybe the crash nodes are important. So uniform actually cares about the crash nodes. So let me explain the intuition. So let's say the broadcast is doing a real world action. Like I'm sending a message to a printer and it's printing. Or I'm sending a message for a bank account. Okay, and it's withdrawing money. But there's like an ATM machine and the money is actually coming out of the machine. Or I'm launching a missile. That's a more dangerous example, huh? So I send a broadcast to the missile silos and they have to launch missiles. Now, okay, I broadcast. And then the sender fails. And no correct node delivers the message. But what about the failed nodes? What if the missile silo, the computer crashes? Did it launch the missile or not? Did the printer print something? What if the printer node, the computer crashes? Well, the reliable broadcast doesn't say anything about that, okay? The failed nodes, they might or might not deliver the message. So assume the sender fails, no correct node delivers. But what about the failed nodes? Well, reliable broadcast says nothing here, because it says nothing about the failed nodes. But maybe we want to know about the failed nodes. So in this case, the failed nodes is actually important, okay? There's money coming out of the ATM, like real money. We want to know whether the money came out, okay? Or whether no money came out. We want to know that. So we want to know something about these failed nodes, because maybe the money came out before the node failed. Huh? Maybe it did. But reliable broadcast will not tell us. So this is why we have a more powerful, a stronger one called uniform reliable broadcast. This is going to tell us about failed nodes too. Okay? So uniform reliable broadcast, it says, if the failed node delivers, so the node delivers and it crashes just after. If that happens, then everybody must deliver. Of course, the correct nodes. Okay. We can't resuscitate dead nodes, but all the correct nodes have to deliver. That means if a failed node delivers, that means if a node delivers and then it crashes, then all the correct nodes have to deliver too. Okay? That means if I'm a correct node on ATM machine or on the missile silos, I'm a correct node and I did not receive a message, then I'm sure that the missile was not launched. Okay? Because if the missile was launched and then the computer crashes, then I would have gotten a message too. Okay? So I can be sure when that this real world action did not happen. Okay? So uniform also is doing this. It's worrying about the failed node. So I have a failed node here, so P3, it delivers, and then it fails. So this case is exactly the case I'm worried about here. And reliable broadcast says nothing about this, because reliable broadcast only looks at correct nodes and not failed nodes. So uniform reliable means that I'm also worrying about this case. Okay? So that's the uniform. So uniform reliable broadcast has almost the same specification as reliable. So it has these properties again. So 4 properties. The first 3 are the same as reliable. Then the 4th one, there's only one word difference. If a process delivers M, then every correct process delivers M. Here, we just remove the word correct. Here, it's if any process, even a crashed one, okay, delivers M. If anybody, even a crashed one, like this case, then every correct process delivers M. So uniform agreement means that the failed and the correct nodes are agreed, okay? When it says uniform, it means I'm also looking at failed, and correct. So that's why it's called uniform. You can say it's a weird terminology. Yeah, maybe it is, but I didn't invent it, okay? Uniform means this, that I'm worried about failed nodes. So when people talk about uniform reliable broadcast, then you know what they mean, huh? That the failed nodes are important. Okay, now let's write some code. Now we've seen the specification, now we're going to write the code for this. So yeah, so best effort broadcast. So this one is very simple. We're going to use the perfect channels. Remember we did the channels where we have perfect point-to-point links, where you send exactly one message if the 2 nodes are correct. We're going to use that. And we're going to make a for loop to send a message to all the nodes. So basically, the broadcast nodes send message to everybody else. Okay? So this is fine. I'm not even going to show you the code. Best effort is so simple. Okay? So no creation, no duplication. It's guaranteed because the perfect channels guarantee it. Okay? And the sender doesn't crash. Everybody receives the message because the channels are perfect. So the proof is easy. Okay, so that's the easy case. That's best effort broadcast. Now let's look at reliable. The all or none. Okay, we're going to make several implementations. And the first one is going to use a perfect failure detector, P. Okay, and so we're going to use best effort broadcast and a perfect failure detector. So what we do when we broadcast, we do, so this thing, so it looks like this, huh? If you want to write it as a layered system. I have my reliable broadcast algorithm. It's built on top of best effort broadcast and the perfect failure detector, huh? So it looks like this, huh? So the reliable broadcast is using best effort broadcast. It's also using the perfect failure detector with the crash messages, huh? To know when there's crashes. So in order to broadcast the message, I do first the best effort broadcast, Okay? And then when I get a deliver, so when the message comes back, I do a reliable delivery, but I also save the message so that there's no duplicates. Okay? Now, how does it work? How does it do all or none? So let's say it sends a message to one node and then it crashes. Then the sender crashes. Well, the node that receives the message is going to do the work. It's going to relay. So if the sender crashes, the other nodes will detect this and relay the messages. So if P1 crashes, P2 receives the message, then P2 is going to be like the new sender. Okay? But this can happen in two ways. Huh? So maybe I receive the message from S, and then I detect that S has crashed after that. But it can be opposite, huh? There's no order here. Maybe I detected the message, this sender has crashed, and then I get the message after. This is perfectly reasonable, huh? Because there's no speed. Maybe this crash detection goes very fast, but this message, it was actually sent before the crash, but maybe it's slower than the crash detection, huh? So these are the two cases we have to handle, okay? Both are possible, huh? Because it's not guaranteed that the message is going to be there before the crash, huh? No guarantee. So we can have both cases. So the code has to handle both cases, okay? So I explained why case 2? Well, because we're in an asynchronous. Well, basically, we're in a system. We don't know. This plug is not very reliable. It's not very reliable. So there's no FIFO. There's no guarantee of message order. That's not part of the model. Even in the synchronous model, that's not true. Right? Even in the case of synchronous, where there's an upper bound, there's no guarantee that the crash detection will be after the message. Huh? No guarantee. So we have to handle both cases. Okay. So here's the code. It's 2 pages of code. So this is the first algorithm that's kind of non-trivial that we're doing. Huh? So this is it's using these two. So remember there's an init event. So each node remembers the messages it's delivered, empty set. It also remembers the nodes that it thinks are correct. So pi is the set of all nodes here. Right? So it starts by thinking all nodes are correct, P1 up to Pn. And then it also remembers where the messages come from. So for all messages, all nodes in pi, it's empty. Okay, so it starts here. I do a reliable broadcast. So I'm doing this. Huh? What it does is a best effort broadcast. Okay? It does a best effort broadcast. And that's how it starts. And then, okay, and then there's the result. Then there's the rest of the code. There's 2 possibilities. It can receive a crash message, or it can receive best effort delivered. Okay? So it can either receive a crash message from the failure detector, or it can receive best effort delivered. So how does it work? So when it receives the crash message, first of all, PI has crashed, so I remove PI from the set of correct nodes. Okay? And anything we have received already, so from PI is the messages we have received from PI. We redistribute them. So here it's the node takes over the work of the crashed node. So PI has crashed, well then I'm going to do the best effort here, broadcast. Because we're not sure that the crashed node is able to send everywhere, so we take over this one. Okay? And the other case, so this handles case 1. Okay. Case 1 is where we receive the message before the crash notification. Okay. But if you receive the crash notification first, and we don't have a message yet, and then we receive the message later. So best effort deliver here. So if we get a best effort deliver, if we have not delivered yet, so this is basically getting rid of duplicates. Huh? So if we haven't delivered yet, we add it to the delivered set. We add it to the set of messages that we got from PI, and then we do a deliver. Okay? And here's where we handle the other case. If the PI has crashed, we have to do the best effort broadcast again. Okay? So in the case where the crash comes before the message, that means when we get the message, the node is already crashed. That means we have to do this. So in both cases, when there's a crash, we have to do a best effort broadcast. Huh? So if we see that PI has crashed, we have to do a best effort broadcast. We have to, because the crash node, we're not sure it did all the work. We have to take the work over here. So this is the full algorithm. That's it. 2 pages. Not so complicated, huh? This is actually a very sophisticated concurrent distributed system. Okay? Because it's completely concurrent. Anybody can do broadcast anytime they want, on any node they want. It also is fault tolerant. Any nodes can crash at any time, and the algorithm will still work. So this is actually a very sophisticated algorithm, okay? Maybe it looks simple. What do you think? Does it look simple? It's logical at least, right? It's logical, huh? And then we can prove it by looking at the specification and looking at this code. Okay?
Sorry, why they store for future?
It's because
that is before the crash, the SM.
it's because if there's a crash, if a node crashes, we get a message from a node, okay, and the node crashes, then we have to do the broadcast ourselves, because the node that crashed maybe didn't do all the work. So if we have to keep track of all the nodes, all the messages we get from PI, because maybe later on we find out that it crashes. Okay? Maybe we get this before, maybe the crash message comes only later, okay? So when the crash message, so I get a message from PI, and later on I see, but PI has crashed. That means maybe PI did not do all the work. That means I have to do the work, okay? So the poor, stupid PI is not able to do the work. And the only way I can do it is if I keep track of all of these. So whenever I get a message from PI, I have to keep it. Because maybe later on, I find out that PI has crashed. You see, huh? So it's just in case. Maybe I don't need it, huh? But sometimes I need it, huh? To guarantee. See how it works? It's a little bit subtle, huh? So it's not that simple, this algorithm, huh? It's actually doing some subtle things, huh? Yeah?
And so if a node crashes after sending a message,
Yeah.
all the other process that receive the message will broadcast
Yes.
it to guarantee that everybody has
Yes.
it.
So you might have the message arriving more than once.
Yeah.
You have to be kind of conservative. That's why there's this to make sure you don't have duplicate deliveries, you keep track of it. So you only deliver once. But because of this, because of crashes, you might have duplicate messages. Because maybe P1 crashes, but P2 and P3 are both detecting it. And they both do broadcast. Because they both have to do broadcast, because maybe P2 also crashes. And maybe only P3 is left. Or maybe P3 crashes, only P2 is left. So they don't know that, so they both have to do the broadcast. Which means that P4 might get the message twice, or 3 times, or once. So you have to keep track of duplicates. So the algorithm is actually, it has to be conservative, like that. Huh? Otherwise, it doesn't guarantee, because crashes can always happen. Maybe late, maybe everything seems fine, and at the very end, when everything is basically almost done, I find out that P1 has crashed. Well, then I'm really in a problem, because maybe P1 did nothing, almost nothing of the work. So I have to do a broadcast.
But isn't it highly memory consuming?
Yes.
To keep track of all the
Yes,
messages?
it is. And we can do optimizations, of course. So this is a correct algorithm. You can do optimization to reduce things, huh?
Yeah, because there we have to keep track of, we have to keep all the message.
Yes, you're paying the price for reliability. Huh? Reliability is not cheap. You're paying the price, which means you have extra memory, extra messages. It's redundancy. Yeah? If you want the system to be reliable, you have to do extra stuff. Okay? Yes, and it can be expensive. But this algorithm is actually not that expensive. It's only paying the price when it gets crash messages. If there's no crash message, it's actually very cheap, because it's only doing one best effort broadcast. It's when you start getting crash messages that you start paying. So you only pay in the case of failures. That's actually not bad. So when things fail, people are usually willing to pay to make sure it's working well. Huh? And when you don't fail, you don't want to pay. So that's actually very reasonable. It's actually nice. But yeah, if there's a lot of failures, it's going to be expensive. Yeah, exactly. So here's, remember case 1 and case 2 here? So here we have P1. It does a broadcast, crashes. P2 detects the crash, and then it delivers after. It's very possible, huh? So this crash detection comes before the delivery, huh? So this is what we called, what did we call it? So this is what we called case 2, I think, huh? Yeah, case 2. And the other one, see here now I changed the order. P1 broadcasts, delivers here, and then it detects crash of P1. Well, in this case, P2 has to do the broadcast, huh? Because maybe P1 didn't do all the work, and actually it didn't, huh? P1 did not send anything to P3. So it's P2 that has to send to P3, yeah? Okay? So you have to handle both cases, huh? To make sure that it's always working. Okay? So that's case 1. We can prove it. So I'm going to make some reasoning. So the real thing to prove is RB4. So the first 3 are basically the properties of best effort broadcast. And since we're doing best effort broadcast, we're going to satisfy that. But it's the 4th one that's really the tricky one. If a correct node delivers M, then every correct node delivers M. Basically, we have to prove that if one correct node delivers, then they all deliver. It's not that simple to prove this, okay? But I mean, it's not so complicated either, huh? We have to do a little bit of reasoning. So let's say PI broadcasts to PJ, okay? PI broadcasts to PJ. So there's 2 cases. If PI is correct, then everything's fine, because the PI is going to do all the work. So if PI is correct, everything is fine. Best ever broadcast ensures correct delivery. So if PI is correct, no problem. But what if PI crashes? Well, if PI crashes, PJ will detect it, because I have a perfect failure detector, completeness. So I'm sure, okay, PJ is going to detect that. And then PJ is going to do the best effort broadcast. And everybody will also get it, okay? You see, in the 2 cases, we're fine, huh? Either PI does all the work, or if PI crashes, PJ is guaranteed to detect it, and then PJ is going to do the best effort broadcast and do all the work. See that? So it's actually PJ is taking over the work from PI, and it's guaranteed because the failure detector is complete. It's always going to detect the crash. Okay? This is actually a proof by induction, mathematical induction. You see why it's like that? I mean, I'm leaving a little bit out here. It's actually a proof by induction, which means that there can be many, many steps. You see why it's proof by induction? What is induction? Induction is that you take a case and you reduce it to a simpler case, and eventually you go to the base case. Because this, what if PJ crashes? Well then, PK is going to detect that and do the work. But what if PK crashes? Well then, PL is going to detect that and do the work. So we're actually reducing to a simpler case. There's like a chain. In the worst case, it's like a chain. PI sends a message to PJ, and then PI crashes. Boom. PJ sends a message to PK, and then PJ crashes. Boom. PK sends it to PL, and then PK crashes. So you can actually have a chain, and it's only the guy at the end of the chain who has to be correct. You see that? So here we're actually reducing the chain by one length. So this base case, and here in this case here, we remove one link in the chain. And now we're talking to PJ. So PJ is like the new PI here. And then eventually we come to the base case. So it's actually induction, because you can actually have many guys connecting to each other. You see that? In the worst case. And that's why you guarantee the all or none. You see, all or none is not that simple to guarantee. But it's kind of neat, right? It's a clever algorithm, right? What do you think? It's clever, huh? So with this you get actually very strong thing, So this one is called lazy reliable broadcast, because it's like doing the minimum amount of work. Because we're using this perfect failure detector, and we're only rebroadcasting if we really have to. Okay? Okay? Now, the million-dollar question, what happens if we replace P with eventually P? What if we replace this P here by an eventually P? Does the algorithm still work? What do you think? There's the question. So we have this really nice algorithm. So we're detecting a crash, and PJ takes over the work with PI when it detects the PI crashes. But what if we have eventually P? It means the failure detector can make mistakes. It means the failure detector can say PI has crashed even when PI has not really crashed. Okay? It thinks that PI has crashed. Is that okay? Does the algorithm still work? What a nice question, huh? Isn't that a nice question? This is the kind of question that's really at the heart of this course, huh? Does it still work? Can you imagine what happens when you replace P by eventually P? So you have to be very clear. Eventually P makes mistakes. That means PJ thinks that PI has crashed. That means PJ will do a broadcast even though it doesn't really have to, because PI is still doing the work. Is that okay?
If it broadcasts more than it should, it's okay, but if it doesn't broadcast, if a node crashes, then...
But it will broadcast, huh?
Yeah, but if it doesn't detect that...
No, eventually P is still complete, huh?
Okay,
So if the node crashes, it will eventually tell me. But sometimes it thinks the node crashes, didn't really crash. But eventually P is complete still, huh?
Okay, but then
it's eventually complete. It means that if the node really crashed, it's going to tell me for sure. So it's never going to do less.
Then it's just more expensive.
It's just more expensive, exactly. So eventually P, if it makes a lot of mistakes, it's just going to make the system slower. But it's still correct. Okay? What happens if we replace it? it only affects performance, not correctness. See that? If PJ broadcasts and PI is still doing the work, that's just more messages. But it's not incorrect. So it only makes the system slower. It still works. So this algorithm also works for eventually P, so we're good. We can run this on internet. Okay, we're good. We're golden here, huh? Okay?
But is it in some cases more useful to use eventually P than P?
In real life, it's almost never possible to have P. On internet, yeah, you can have it if you know everything, if you're like in a cluster. Or a local area network, sometimes you know P. And on the internet, you almost never know this. You're almost always in this case, in real life. But in the course, I don't want to give you the complicated algorithm. We're going to always start with P, and then we like evolve towards eventually P. Because these algorithms are always very simple, the P algorithms, okay? And a little bit of cleverness, and we can usually get an eventual P algorithm out of there. So this is the one we really want in practice, huh? The real internet systems like used by Google and Facebook, they use this, huh? They're not going to broadcast that, tell everybody, okay? They're going to say everything is very simple, and it's wonderful, and we're great, and everything. But they're using complicated algorithms based on eventually P, okay? They're all doing this. So this case, it works. So that means if we make mistakes, that means that it's just going to be a little bit slower, but it'll still be correct. But you can actually go farther now. Can we modify this algorithm, so the lazy, to not use P? So no failure detector at all. Not even eventually P. If we're allowed to make mistakes, the ultimate mistake is that always thinking everybody's failed. That's the ultimate mistake. Will it still work? Will it still work?
If everybody has to broadcast everything every time, it's too expensive.
What do you mean, too expensive? How expensive? Tell me. Make a calculation. Every node has to do one broadcast. If I have n nodes, that makes n broadcasts. That means n squared messages. Yeah. So it's not really so scalable anymore. N squared. But it's only n squared. That's it. It's not infinite. It's not exponential. You pay, if you remove completely the failure detector, it's still correct. And it'll take n squared messages. Okay? Assume all nodes failed and do best effort broadcast as soon as you get a message. Boom. Assume that all the nodes are failing. So you're always making a mistake. But it'll be correct, huh? So you don't even need any failure detector. You can always still use it. Of course, it's going to be slow. The better your failure detector is, the more efficient it will be, okay? If you have P, it'll be very efficient. And especially if you have no failures, P will know that, and it'll be extremely efficient. Only n minus 1 messages, okay, for n nodes. So it's very efficient in the case where you have no failures and a very good failure detector. If you have more and more failures, it gets slower, and if your failure detector gets worse, it gets slower. But the worst is n squared, okay? The worst is n squared. So here's the code. I think it's only one page, huh? Yeah. So the eager one, the one that has no failure detector, is only using best effort broadcast. This is the full code of the algorithm, okay? It's not so much code. Look, one page, and it's even in a big font. Okay, if I do a broadcast here, I will immediately deliver. Okay, it's been delivered, and I will do a best effort broadcast. And then if I get a best effort deliver, I will deliver it. If it has not been delivered, I will do a best effort broadcast. So every node is going to do a best effort broadcast. Okay, n squared. And best effort broadcasts. So this code is very simple, and it's correct, and it does not need a failure detector. Of course, it's inefficient. There's always some price to pay. So the failure detector actually, the role of the failure detector here is an efficiency role. You don't need it for correctness. That's not always going to be like that. We're going to see algorithms where it's not so easy to go to eventually P, but this one, it's okay. Okay, the correctness of the eager one, wow, this is pretty easy. We can prove it then. We need to prove the fourth property. If a correct node delivers, and every correct node delivers, okay, if a correct node delivers, then it will do a best ever broadcast, and all correct nodes will get that message. So it's obvious, okay? Don't even need to do induction here, okay? Now we go to the next step. We have gone from P to eventually P, and it's okay. Now we're going to try to make a uniform, reliable broadcasts. So let me recall to you what that means. So uniform means is that even when a failed node delivers, all correct nodes deliver. Is that the case here? If a failed node delivers, will all correct nodes deliver? Is that the case in this algorithm, or in the lazy algorithm? Is the proposed algorithm uniform? Okay. So let's say this node delivers. Okay, it delivers, and then it fails. Right here. Before doing the broadcast. But maybe all the other nodes are correct. So here I have the case of a failed node delivering, but nobody else delivering. So that's not uniform, right? It's not uniform, okay? Uniform is not so easy usually to do. Huh? Uniform, it's not uniform, huh? No. If the sender immediately delivers and crashes right away, then only this one, P, will deliver and nobody else. Not uniform, huh? If a failed node delivers, all the correct nodes have to deliver. But it's not the case here. So uniform is usually very tricky because we have to handle the failed nodes in a special way, okay? We have to handle these guys specially, whereas this algorithm doesn't really do anything special with the failed nodes, huh? No. If a failed node delivers, then every correct node must deliver. So how can we make sure about that? That sounds hard, huh? If a node delivers and it fails right after that, how can the other ones know that it has delivered? Because they have to deliver too then, huh? How can that work? How can that work? What do you think? This is actually pretty tricky, huh? If I deliver and I fail just after, I mean, how do the other nodes know that this failed node has actually delivered? How do they know? I mean, there's no messages leaving, nothing. It can happen right after the delivery, huh? But if that happens, they all have to deliver. How can we handle this? This seems very tricky, huh? What do you think? It's tricky, huh? Well, it is tricky, but you have to be a little bit clever. Basically, the way to handle that is to be really conservative when you deliver. Only deliver when you're sure that all the correct nodes got the message, and not before, okay? In this algorithm, I deliver right away. I don't care about the correct nodes or not, huh? I get a message, I deliver it. So I'm delivering very fast, boom, boom, boom. But here, I have to be more conservative on the delivery, yeah? Because I can fail right after. So usually I do here is I actually delay the delivery until I'm sure that all the correct nodes have got it. Yeah?
But if we wait for the others to be to have delivered, won't everybody be stuck waiting for the
No, we
others?
don't have to wait until they deliver. We have to wait until they have received the message. We have to get an acknowledgement from them. So we have to wait until we know that all the correct nodes have received. So when a correct node gets the message, it acknowledges to everybody else. And when I receive acknowledgements from all the correct nodes, then I'm good.
Okay, so everybody has to receive the message, send acknowledgement, and when he received acknowledgement from everybody, then he can say, okay, deliver.
Yes, exactly.
Okay.
That's basically the idea. Okay? And then it's uniform. You see, uniform is kind of a more complicated thing, huh? Because failed nodes are tricky things, huh? All correct nodes. So this is a necessary condition for delivery. I only can deliver on my node if I know that all the correct nodes have gotten the message. So how do we know that? Well, we basically wait for acknowledgement from all of them. Okay? We collect acknowledgement. And as soon as we know that all of the correct nodes have gotten the message, we're allowed to deliver. And basically, we can also have crashes. Huh? So the set of correct nodes can be getting smaller, of course. Huh? If there's a crash, then we don't have to wait for acknowledgement from a crashed node, of course. Huh? We collect acts from the correct nodes that got the message, and when we get enough acts, we get allowed to deliver. So we need another data structure. The set, and it's indexed by the message. So it's nice to have pseudocode. Huh? When you implement this, you have to be careful here, because I'm indexing by the message. This is the set of nodes that acknowledge the message M. So usually messages have unique ID, so I can index by that ID. Okay? So the pseudocode is going to be not so complicated. So when all correct nodes have acknowledged that they got the message, and I can use a perfect failure detector here, I have a function here called canDeliver. And it's true when I'm allowed to deliver. So when all correct nodes have acknowledgement, which means that the set of correct nodes is a subset of the set of nodes that acknowledge. All correct nodes have acknowledged. So this is the Boolean condition. Huh? When this condition is true, I'm allowed to deliver. All correct nodes have acknowledged. If there's any correct node that is not acknowledged, I have to wait. Okay? So this is how it works. And the algorithm is a little bit more complicated here, because I have this ACK. I have this ACK, this acknowledge thing. So here I have uniform reliable broadcast. So I do a broadcast. I'm not allowed to deliver yet, but I have this pending set. I get the message, and I wait until I'm allowed to deliver. Okay? Then I do best effort broadcast. I do best effort deliver. Okay, I get a message from PI. Well, I know that PI has got M, so I add it to ACK M. Okay? If the message is not pending yet, I add it to the pending. So pending, it keeps track of all the messages that I got, but I'm not allowed to deliver them yet. Okay? And I do another best effort broadcast. And finally, sometimes I'm allowed to deliver. So if I have a pending message that has not been delivered yet, M not in delivered, and I have this canDeliver condition, and I'm allowed to deliver it, which means that all correct nodes have acknowledged, then I deliver. Okay? See, this is a funny rule because there's no message here. It's only Boolean condition here. But these variables are updated in the other rules. So whenever I execute one of these other rules, this one might become true. And when this becomes true, I can deliver. So basically, I wait until all the correct nodes have acknowledged to me, and then I deliver. So this one is more complicated than that. Now we start getting into kind of complicated algorithms. Okay, avoid resending, deliver when all correct nodes are acknowledged. Okay, so basically that's it. There's also a few other rules that I don't. So there's also the set of correct nodes, okay, which is reduced when there's a crash, a perfect failure detector. But that's basically the code for uniform, reliable broadcast. So what do you think of that? Now we're really getting into distributed algorithms here, huh? This is actually a very sophisticated algorithm if you think about it, huh? Probably you have never written a concurrent program as sophisticated as this one, because this one is concurrent, so it's able to handle any number of broadcasts happening concurrently. It's from any node. It's able to handle failures, and it's uniform. That means it's able to guarantee this complicated condition that if any node delivers, all correct nodes deliver, even the failed nodes. So it's a very sophisticated, concurrent, distributed, fault-tolerant algorithm. Huh? Probably you have not written an algorithm so complicated as this one. So now you can see why it's so nice, this notation, huh? And the fact that we do everything in layers, huh? It actually makes it so we can understand this. This is actually one of the best ways of writing distributed algorithms, because even such a complicated algorithm, you can actually think about it and see how it works, okay? Using this very nice concurrent condition action rules, and using these very simple properties that we defined, and the layered system. So each layer is only doing one little thing. So this is built on top of best effort broadcast and the perfect failure detector. So the URB algorithm also is built on top of these two. It's built on top of these two as well, if you want to see it. Also, another reason why this algorithm is simple is because we focus on correctness, and we're not doing all these optimizations. So we have this delivered set, the pending set here. You have to also garbage collect it, okay? The delivered set, you have to remove things if you want this to be really efficient. Well, we don't worry about that here. We're only worrying about correctness and message complexity, not about the data on the nodes. Okay? That's another reason why this algorithm is simple. If you want to turn this into a practical algorithm, you have to do garbage collection. You have to do more work. But we're not doing that here. Okay? So, of course, you can also talk about the correctness here. Here, it's almost the same as before. Okay? Okay? If a correct node, it's a little bit more complicated, but maybe I don't go into it right away. Let's see, what should I say? Okay, we can do more discussion of it. But I think maybe I stop here, and next week I talk a little bit more and we do more sophisticated stuff, okay? Like causal delivery, for example. But you get the intuition, huh? You see how it works, huh? Get the idea of how it works, huh? And you also understand for reliable delivery how we can go from P to eventually P, yeah? You see it, huh? Because it only affects efficiency here, huh? But uniform has to do more work because we have to be very careful when we deliver. We're only allowed to deliver when we're sure that all the correct nodes have gotten the message. Otherwise, we can't guarantee the uniform property. Okay? Okay, so...
Sorry, can you repeat the last sentence?
Yeah,
You know,
the
the
uniform property.
uniform.
Yeah, the uniform property, it means that if a node delivers, all correct nodes have to deliver. But it can deliver and fail just after. So how can we make sure that the correct nodes will not deliver? It means we have to be very careful. We only allow to deliver when we know for sure that all the correct nodes already have the message. Okay? So this is, we have to be careful. That's why we need this condition. If we have to be very careful when we deliver. In this algorithm, we deliver immediately. But the uniform algorithm, we slow down. We don't deliver so fast. Huh? We have to be a little bit careful about the delivery here. Huh? Because delivery now is a very strong thing. Huh? If we deliver, then all correct nodes have to deliver too. So we have to be careful. See how it works? The uniform property is you have to do some special work for that. Huh? Okay? Okay, so let me stop there. So now you can see that the course is getting very interesting. Huh? Now we're seeing good stuff. Huh?